Good morning, everyone. My name is Fred Guanel. I am the co-lead for the Hazard Mitigation and Resilience Plan update for the US Virgin Islands. There is an echo. Jose, do you mind muting yourself? There is a bit of an echo. Really appreciate everybody joining us for this very exciting webinar about the earthquake risks and what to do to prepare for earthquakes in the Virgin Islands. So I'm just going to provide a little bit of background for why it's important, and then I will introduce the presenters for today, and then they will go and make their presentation. And after that, we're going to have some general Q&A. So what is an earthquake? An earthquake is usually generated when different plates sort of move against each other. There's different ways that the different plates can move, and you can see it on the left-hand side. Michael, would you mind muting everyone, please? Mr. Charlesworth, would you mind muting yourself?
Oh, hi, good day. My name is Carlton Charles Jr. from the Virgin Islands Port Authority.
Oh, thank you so much. Would you mind muting yourself, please? Thank you so much. Yes, so those are the different ways that plates can move. And when you have any type of movement between plates, this creates a series of waves. Those are called seismic waves. And those seismic waves, basically by moving through various rocks and matter that make the earth, will create a movement at the surface. This movement at the surface then goes from no movement to sub-movement. So as soon as you have this type of phenomena, you have what's called acceleration. So we tend to really sort of quantify the severity of earthquake, among other things, by looking at what's called the peak ground acceleration, or PGA. So that's something that people talk about a lot when they look at what is the earthquake risk for a particular location. So what is the maximum peak ground acceleration that can occur is basically the question that is being asked. So for us in the USVI, we are in the Caribbean. And as you can see here, there are a lot of plates and a lot of faults. Faults are basically fractures between plates, basically opportunities for plates to move against each other, or for different entities, that make the crust to move against each other. And that movement creates a wave that creates what we feel as an earthquake. So as you can see here, we've had a lot of earthquakes. So there's a lot of plates. The biggest one is this one that causes a lot of very important earthquakes. But there are a lot of other plates and microplates in our region that, as you can see from all the dates, have created major earthquakes through our history. So this here is another representation of all the earthquakes that occurred around us. And those are with magnitude greater than 4.5. So you see Puerto Rico definitely affected. The Virgin Islands has been affected. The BVI in particular has been also quite affected. All those little stars and dots, as you can see here, represent different earthquakes that occurred. And as you can see here, the number of, we've had a lot of earthquakes of magnitude greater than 7 that can be quite devastating. The more recent one that happened in Puerto Rico in 2020 was approximately 6.5. So that earthquake that caused a lot of damage is actually not a major earthquake compared to what happened in the past. And what's interesting about these dates is that those earthquakes can create tsunamis. So the 1867 earthquake and the 1918 earthquake generated tsunamis that created further havoc on the islands. So I talked about PGA earlier. So this is a map of PGA, of peak ground acceleration. That really sort of gives us our risk. How dangerous can earthquake be in a territory? So this is St. Thomas, St. John, and St. Croix. This is Puerto Rico. The earthquake that Puerto Rico experienced last year were around this region. And you see the amount of damage that occurred in that region based on all the reporting that occurred. It turns out that the largest earthquake that can be experienced in our region can actually be the more damaging if those large earthquakes occur, say, in St. Thomas or St. Croix. You can see that the peak ground acceleration that has a 10% chance of occurring every 50 years is quite large compared to most of Puerto Rico for St. Thomas and St. John. It's a bit lower for St. Croix, but still it's not zero. We are in a very active, dangerous region for earthquakes. This is an event that has fewer chance of occurring, 2% probability of being exceeded in 50 years. But again, those earthquakes can be quite damaging in terms of PDA. So if you don't quite know what that means, let's compare it to the US. So this is the map of 10% chance of occurring in 50 years for the United States here. So region in, orange, yellow have, a PGA of 15, 20, 40. We in a VI have, 0.15, 0.2, and 0.25, 0.30 for St. Thomas and St. John. So what that means is that we need to look at the yellow to maybe the orange, light yellow to the sort of darker yellow and orange. It's not as bad as some places in California, but it is comparable to, a lot of places in California, Washington, and Oregon State. And so this means that the earthquake that we have, again, can be quite damaging, especially if we compare it to what has happened in other places in the United States.
Greg, the peak ground acceleration, is that what is that on the Richter scale? If you
so I will let my colleague who will give their presentation address this in a second. So if in terms of, what does that mean in reality? So those are pictures that were taken in Puerto Rico after the major earthquake that they experienced. And you can see the type of damages to houses, to buildings, the type of damaging to buildings that are built on stilts. And what can happen, the building can look fine, but the support structure are quite damaged, as you can see in those pictures. It can also happen to infrastructure. So here, those are the pilings for a highway that is damaged, that will then threaten the integrity of that structure moving forward. Those were taken in some, public plazas, and you see the type of displacement that occurs, mostly because of the type of soil that, was below it. And hopefully my colleagues from Puerto Rico and Trinidad will discuss more how this can happen, given the type of soil that you have. So what does that mean for the VI? Well, as I mentioned earlier, we live in a very dangerous zone for earthquakes. Earthquakes have happened in the past, and they can happen anytime. They can happen today, tomorrow, or they can happen 10 years from now. But they can be quite damaging. And when we look around in the VI, we then ask questions, and hopefully our guest today will help us start, creating answers for these questions. So we see buildings that are made out of masonry, and the support structure are basically concrete blocks. From my point of view, that might be a problem, but maybe it's not. We also see structures that are made of wood, structures that are made of reinforced concrete, but the reinforced concrete is starting to degrade, probably because of the quality of the masonry when the structure was built. We also have very old structures made out of stone and concrete on top. There's all type of different of structures that we have here in the VI, and those have different ability to resist or completely collapse during earthquakes. We also have very steep terrain in the USVI. This is also not uncommon in parts of Puerto Rico because it's also mountainous. But we probably have a higher percentage of structure on steep slopes on St. Thomas and St. John because that's what our topography is in majority. So you see a lot of structures, multi-story building made out of different materials, different quality construction type that are built on very steep slopes. And here they're building a new structure on a fairly steep slope. I sometimes wonder how they get the equipment down there, to be honest. And you have a lot of structures that are 1 or 2 story high max, but built on stilts. And those stilts are 1, 2, 3 structure high, 1, 2 structure high, sometime, or 3 level high. So when I see those pictures and this type of building, it really sort of makes me wonder exactly, is it safe? What does that mean for, if we have an earthquake, what does that mean for the stability of these structures? Maybe it's okay, but this is the question that, we're going to be asking ourselves today. And, if it's not okay, what can be done to either remedy, mitigate the problem, or to sort of ensure that it doesn't happen in the future. So today I have, very excited, and hold on one second, I need to very excited to have 2 great speakers to talk about earthquake risks in the VI, and what does that mean for us to sort of either mitigate against earthquake risk, or really in the future prevent earthquakes from creating any type of damage to the homes and the infrastructure that we have here in the Virgin Islands. So we have 2 speakers. The first speaker is Dr. Jose Martinez. He is a professor of civil engineering at the Civil Engineering and Surveying Department at the University of Puerto Rico at Mayagüez. Dr. Martinez used to teach courses in the earthquake-resistant design of reinforced concrete structures, and is now in charge of the Puerto Rico Strong Motion Program. So Dr. Martinez will be our first speaker. We're going to have 5 minutes of question and answer, just, very quick question that, some people in the audience are, excited and eager to ask immediately. But we will move very shortly to our second speaker, Dr. Richard Clark. Mr. Clark is a senior lecturer at the University of the West Indies in Trinidad and Tobago, the St. Augustine campus. And he was the former head of the Department of Civil and Environmental Engineering at the University of West Indies in Trinidad and Tobago. He is a research and professional structural engineer specializing in performance-based seismic design, seismic retrofitting, innovative structural material, and he's also spending a lot of time training of professional engineers. So I really thank both Dr. Martinez and Clark for their time today to discuss with us earthquake risk and how to prevent damage during those events. And without further ado, I will turn it to our first speaker, Dr. Martinez.
Okay, thank you very much, Greg. Let's see. Everybody watching my screen?
Yes, we can see it.
Okay, perfect. Well, my presentation is entitled Structural Details That Make Structural Performance More Vulnerable to Earthquakes. Let's see, since 1985, basically, I have been doing some recognized visit to sites where earthquake strikes. So I have getting a lot of pictures of those areas, and I have also included pictures from other earthquakes that I haven't visited them. But we have been learning several lessons about this visit. That's basically what I want to present. I'm just going to present about 8 points which are follow the friction pile versus bearing pile foundation, what the difference is and how the structure behave. Structural hammering, that is very common back in Mexico. A drastic change in structural stiffness, which is very common all around the world. Structural asymmetry or non-symmetric structure, basically. Structural expansions, which is very difficult in reinforced concrete, but not that bad in structural steel structures. A similar period of vibration of the ground and on the structure. The seventh one is this deficiency in the distribution of ties in joints or columns. And finally, the short column effect, that is something that scares a lot of people here in Puerto Rico, especially in schools, okay? So you might wonder, in the case of this bearing pipe and friction pipe foundation, you might wonder why some structures sink during earthquake, like this building in 1985 in Mexico, which sank about 4 or 5 feet, no? While in other cases, like in this one, this was in Japan, 1980, where you see this structure that is basically a basketball court that looks like increased about 18 inches, okay? And what happened is that both structures are built on piles, but what happened is if you have one structure at the left, two similar structure, the one on the left which is in bearing piles, which means that the piles go directly to the bedrock. Okay, so all the weight of the building is transmitted directly to the bedrock. Or you have the other case here are a structure on friction piles. So the load of the structure is being transferred to the ground through the friction between the piles and the ground, no? Okay, so if you have two structures in alluvial soil types, like this one here, most probably when you get the earthquake, the alluvial soil is going to settle down, and then you will have something like this, where the original ground level was this one here, and now because of the soil settlement goes some feet down. So in that case, in the case of the Japan building, you will see that the one that is in bearing piles will look like the building is increasing, it's growing, let's put it that way. While in the case of the Mexico building, which was in pile foundations, then the structure will sink a little bit more because you have this soil settlement and also the structure will settle into the ground, okay? So I'd rather have this case, the bearing piles instead of friction piles. So I usually suggest people to, do your best to reach the bedrock, which I understand is not that simple all the time, okay? In the case of structural hammering, that's very common in Mexico. You see this, the Carlo Hotel, which is the building at the center of this slide. And as you can see, it's one of the intermediate story failed. And it was because of the hammering with the structure that is at the left, this small one, not the big one, because of this small one. These structures are so close to, so near one to the other, that they start hammering one to each other. And in the case, if you don't have the slabs on the same level, one slab is going to hit the column of the other building, that column is going to fail, and then that failure is going to propagate through all the floor, okay? But in other cases, like in the next one, well, this is the detail of the previous slide here, this detail in this hammering here, okay? But also in this one in Mexico, you have an old structure on the left side and a structure what was being built during the earthquake, and they start hammering to each other. Look at that, the level of the slab are basically the same here, okay? So they are hammering one slab with the other here, but the new structure is the one that collapsed from that story to going up, no? Okay? So that's a different type of failure by hammering. And also another type of failure by hammering is when you have this case here in San Fernando earthquake that was in 1971 in California. This was a hospital. This is a five-story structure that have the core of the stairs and elevator here. And there was two different structures completely separated. So they start hammering one with the other, and finally the stairs overturn completely. Okay. In the case of drastic change in structural stiffness, which is pretty common all around the world, you can see this building in 1979. This is Imperial Valley earthquake. The building is a 6-story building, have a very stiff wall from the 2nd floor to the 6th floor here. But then the structure in the 1st floor is supported by columns. And even worse, the columns are not in the same plane that the wall, are shifted in the inner side. So all the shear that come from this wall have to go through the slab and then going down through the column. The structure didn't collapse, but you can see the damage on the columns in the bottom part here. Okay. But not always have that kind of luck. Look at this. This was in Guanica on January 6th. We got an earthquake of 5.8 that day during the morning, and this structure got very damaged. You can see this column here, all these columns on the 1st floor, which is a weak story, it's a soft story. We used to build this way in Puerto Rico because people love to have their garage here, or also in case of tsunami, you can have a better chance that you live higher, no? So in a higher level, I mean. So this was on January 6th, but in January 7th, we got a 6.4 earthquake, and then the structure completely collapsed. And this is so common here in Puerto Rico, having many structures here in silts, basically. These are columns, but many times we have silts, as Brett showed us in his presentation. So you can see, for example, this picture here. This is in Mayagüez, where we have this lighthouse in like, I mean, it doesn't weigh too much, okay, in silts. And what happened, I mean that it's a lighthouse because it's basically wood. You see this roof is basically wood. It's very, very light. It's not too heavy, okay? So we have one professor here, Professor Ricardo Lopez, that he did a research on this type of houses in Puerto Rico. He got a plenty amount of these kind of houses, and he got a model for this type of houses, submit those models to the earthquake records that we have at the building code, and all of them collapsed. All of them. There was not a single one that was standing up. So that's make us to really worry about it. So that's why we prepared this pamphlet, Rehabilitación Sísmica de Casas en Sanco, which means seismic rehabilitation of houses on stilts, that you can find at this web page, okay? And use it whatever, you know, you can read it. It is in Spanish, let me tell you. But anything that know a little bit about construction will be able to rehabilitate your home if you use this type of the thing that we're suggesting over there, okay? In Chile, they solve that problem this way. They don't use silts. Stilts mean they just build, you know, along the tip of the slope, and that's the way they do it. They even have on the some elevator cores here, you can see, okay? Chile have very, very big earthquake every 25 years, okay? In the case of structural asymmetry, what happened is that when you have a structure that is non-symmetric, that would introduce torsion to the structure, and that is a kind of shear that is very difficult to design for, and you try to avoid it. So, for example, this structure on the right side is a rectangular structure that from outside you believe that is a symmetric structure in both directions, in both axes. However, what happened is that the elevator core is at the left side, So when you have the earthquake, this north-south wave will basically displace a lot more the right side compared with the left side. Okay, so you will have a lot of movement here on the right side, and if you have columns in that side, those columns will be need to be able to displace a big amount of inches, you see. So this makes it very vulnerable. The same thing happens in this L-shaped building, no, where in this direction, this building is very stiff. However, in this wing, no, when you have the seismic wave coming in this direction, this will move a lot, this structure here. So what people suggest usually is to have a very big, good structural wall here at the end, or maybe some bracing if it's in the case of structural steel, okay? You can see this case in Managua, Nicaragua. This was December 23, 1972. We have two banks here, Bank of America and Central Bank. The Bank of America is a 17-story building, and the Bank of Central Bank is a 15-story building. Let's see if this one first, American Bank. You see here the drawings, which is a square building, is symmetric in both orthogonal direction, have columns all around the perimeter, and it has elevators and stair core in a symmetric way, okay? So all the damage that this building have during the earthquake were that some tiles fails here on the first floor. So that was no problem at all, okay? But in the case of the Central Bank, which is a rectangular building, having columns in the perimeter and three sides, but then having here the elevator core at the left side of the structure. The structure didn't collapse, but you can see how the stairs end up having a lot of debris here. So the structure have a lot of damage, and at the end, they decide to turn down the last 12 stories. So today, this is a 3-story building, okay, while the other is still there, okay. So it's very, very important to try to reduce the amount of torsion that is introduced in a structure, okay. In the case of expansions, this is a building in Mexico in 1985. This was originally a 7-story building. Later on, the owner got some money and he had 2 more stories. The 2 more stories collapsed during the earthquake. Because in reinforced concrete, to make expansions, it connect them very well to the old structure is very difficult. You know, if you don't know how to do it, you better don't try it, okay? So that happened here. Also happened in this example here. This was a school in 2003 in the earthquake in Puerto Plata in Dominican Republic. This school, the only part that failed was these 2 classrooms that were added later on. You know, they were not original in the drawings. There was a yard here, and later on they decided to build this classroom here, and the connection to the old part was not good, and it completely collapsed. Okay, so in the case of similar period of vibration of the ground and the structure, this is something that happens a lot in Mexico. This is a very particular case in Mexico because the ground in Mexico have a period of vibration of basically 2 seconds. So the structure that have that period of vibration or a little bit less, we have a lot of problem because they can enter in resonance. So that's something that we should always avoid. If you know what's the period of vibration of the ground, you should try to avoid that your building get the same period of vibration of the ground. So to avoid to get them in resonance. In the case that they have the same period of vibration or similar, that doesn't immediately mean that they are going to enter in resonance because resonance needs time, need to have several cycles. And in the case of Mexico, that's happened because the earthquake was very far away, about 400 kilometers far. So the structure here from 6-story building to 20-story building were the more affected one. The small one or the very big ones or the very tall ones were not affected during the earthquake of 1985. Okay. For example, this is the Golden Gate Bridge, have a period of operation of about 11 seconds on the deck. So, you know, they won't have any kind of coincidence with the seismic wave. And neither this pyramid, which is very, very, very stiff, won't have any type of coincidence with the seismic wave. Okay, they can have other problems, but not coincidence in period of vibration. Okay. Regarding the deficiency in distribution of types in columns, this is something very important. I remember when I studied here in Puerto Rico in my bachelor, I never learned how to design the joint. The joints was not part of the class. And it seems that happened also in Venezuela, because this picture was in 1967, and you will see the columns that looks to be in good shape, but there was no connection, not good development length at the end. There was no ties there, and this is the type of collapse that you get when you don't design your joints. Okay, so in 1997, also in Venezuela, they got an earthquake, 6.2 or something like that, in the area of Cariaco. And you see this is the only school in that town of 15,000 people. The first story collapsed, about 33 person died, considering student and the teachers. If you stand here and take a picture to where we are, you will see this other side. You can see this column that collapsed here. There is one story that is missing here. But in the next picture, we're going to show you a detail of this connection here. You will see that they have ties here in the column, 4 or 5 inches spacing. But when you reach the normal beam here, there is no ties anymore here, okay? And the amount of stresses that the joints are submitted is very large, and that might explain why this school collapsed. Another problem in school is the short columns, which happens very, very common, like this one here. This is in Venezuela. This is a shear type of failure, while in the other is in El Salvador. This is a flexural type of failure. And what happened is that when the designer designed the column, usually do not consider the masonry walls that have at the side. So the whole height of the column is this capital H. So you have the force F here multiplied by the H will give you what the moment at the base, no? And the shear is exactly the same at the force, VA in this case. So you design that if it's going to fail, it have to fail because of flexure, because it have to be a ductile type of failure, not because of the shear. So the column might be very well designed, but when you construct this masonry wall here, now you're confining this height of the column. This height of the column cannot move laterally, no? So now, when you have the force of the earthquake applying to the top slab, the shear here will be exactly the same as the force, but now the moment at this point will be a lot less because you have to multiply the force by this small h. So most probably you will reach the capacity of the column, the shear capacity of the column first, than the moment capacity or the flexural capacity. And then you have that brittle type of failure that should avoid all the time, okay? So this is in the Agripina Seda School in Guanica on January 6th after the 5.8 earthquake. There was a column failures here by shear, very clear. You can see this wall, masonry wall with this shear crack and the columns also. And then next day we got the 6.4 and completely collapsed the school, okay? So it's very important in this case that you are in school, you always throw yourself on the floor, put your head under the desk, grab the legs of the desk, and start praying. Okay, because having that amount of desks, most probably those will be able to support the roof. Okay, so that's what I have so far for you. Okay.
Thank you so much for this great presentation. I just want to address the quick question that Kimiko asked during my introduction. Would you mind maybe clarifying the difference between what scientists measure and use for design, which is the peak ground acceleration, versus what is reported, which is the Richter scale, the magnitude on a Richter scale, sorry.
Well, okay, that's the peak ground acceleration will depend not only in the magnitude of the earthquake, but also will depend of how close you are to the epicenter, and will depend also on the type of ground that you are. Okay, so you can have a very big earthquake, let's say an earthquake 9.2, 9.4 that we have in Japan, we have in Chile, but we didn't even felt them here in Puerto Rico in the US Virgin Island. Okay, so there was very big earthquake, but they are so far away that you don't even feel them. Okay, but you can have a small tremor or earthquake of 4.5, 4.8, and makes some houses on stilts to collapse. Okay, because they are so close, the magnitude is very small, but it are so close they can generate a peak ground acceleration big enough to make collapse some type of structures. Okay, so there is not directly relation between Richter scale and peak ground acceleration. Okay, because you have to consider those facts. So what usually is used are what they call the attenuation laws, which are equations where you plug the magnitude of the earthquake, you plug the distance, maybe sometime to the epicenter distance, sometime to the distance to the seismic fall. Also, they consider the type of faults in the type of soil and those kinds of equation, and then you can get a very good estimate of what peak ground acceleration you will get, knowing all those values. Okay.
Yeah, thank you so much. And that's the peak ground acceleration is what you structural engineers are using to design the structure properly and taking and avoid all those type of failure that you mentioned.
Well, that's a very important point, but there are others. Okay.
Yes, definitely.
It's very important also what's the period of vibration of the structure is also. Okay.
Yes. Is there one quick question before we move to our second speaker? Okay, so I'm going to ask Dr. Clark to now make his presentation.
Excuse me. Hello, Mr. Greg.
Yes, go ahead.
Hello, yes, I posted a question on the chat. Basically, any recommendation for concrete homes or addition of homes of rooms were done? And can a retrofit be done to increase safety of the structure?
So that's a really good question. I think that's a question that would fit really well in a general Q&A. So I made note of your question, and I will be asking it as the first question when we open it to the floor.
Thank you.
Thank you.
Thank you.
Dr. Clark, go ahead.
Good afternoon, everyone. Are you seeing the screen?
Yes.
And you hearing me good?
Yes.
Okay, good. So let's begin then. We want to focus on the question, why do bad things happen to buildings due to earthquakes? The issue is bad things happen due to violation of the fundamentals. So this presentation is about what are these fundamentals? What you will find is that you don't have to go into the details of calculations in order to appreciate how to get a building to behave itself. Sometimes when teaching, I like to use the term quality before quantity and concept before calculations. If we understand what is happening, then it is so much easier to appropriately address the problem, especially to use these complex equations in the building codes and so on. So that is what this presentation is about. And the outline of the presentation, we'll begin by looking at the cause and effect from earthquake to building, how a building resists earthquakes, types of earthquake resisting systems for buildings, and these are the 7 factors, the 7 factors for favorable performance of a building under an earthquake: ductility, regularity, multiple load path, short load path, continuous load path. Of course, we'll have a few things to say about a load path, proper connections, and small floor-to-floor horizontal movement. Those are the 7 golden rules. And then we'll wrap up by a brief summary of some of the challenges in the Caribbean due to violations of these fundamentals. So let's begin by looking at the cause and effect from earthquake to building. So we are going in order of the number. 1, earthquake caused by rock slipping at fault. 2, waves move through the soil. 3, horizontal back and forth movement at the ground below the building also. So these are these red lines, forward and backward. To go in the opposite direction, we use dashed lines. Now, this is the critical thing. From the building's point of view, it is not the ground that is the problem. The ground is waking up invisible forces, number 4 here. Horizontal forces at the floors are induced by the ground motion. You can get an example of this. We get an example of this every day, whether you're driving in a car, whether you're playing sports. When you're driving down the road and you slam on the brakes, what happens? You lunge forward. That's why we have airbags. So there is like an invisible force pushing you forward. Likewise, when the building is shaking, invisible forces are generated at the floor levels where the masses of the building are concentrated. And it is that which is actually pushing the building. Yes, we design for peak ground acceleration. Yes, that is acceleration of the ground. But when the building itself is accelerating, the term that we actually use is the spectral acceleration. That's the acceleration of the building due to that generates these horizontal forces, number 4 here. We mustn't forget that we also have vertical forces generated, but they are secondary relative to the horizontal forces. Now, how does a building actually resist an earthquake? Sometimes when you're doing these presentations, we have no choice but to use certain technical terms. So I'm going to bring in one here called the load path. Yes? Now, what is a load path? You can visualize a load path as being something like the flow of water in a river. We have invisible forces flowing through the structure from the point of origin, which is, remember, we said the forces at the floors, and that force flows through the structure as these orange lines that you're seeing here, these wiggly lines. It flows through the floor and down into the elements supporting the floor. What we also notice is that as you go down, the forces actually get bigger. They accumulate as you go from top to bottom. Notice though that the red lines representing the forces outside the building that is generated by the earthquake, they increase as you go from bottom to top. So on the outside, it increases from bottom to top. On the inside, it increases from top to bottom. So let's look at the whole load path. 1 to 2, earthquake force to diaphragm. What do we mean by diaphragm? Well, diaphragm is just a fancy term for the floor slab. the earthquake starts at point 1, flows through the floor slab 2, and the flow is represented by our orange lines, and then it goes down into the supporting elements. I've just sketched these elements as walls, but we'll see in a while that there can be other sorts of supporting systems. So 2 to 3, diaphragm to connection. Jose mentioned just now how important the connection is in reinforced concrete, especially in the Central American region, simply due to poor practice back in the day. But we will also see that steel connections could also be very troublesome. So the path continues, connection to LLRS on upper floor. What is the LLRS? The LLRS is just shortened form of lateral load resisting system. That is what actually is taking the earthquake force into itself. We use the term earthquake resisting system, lateral load resisting system, same thing. Lateral is referring to the horizontal motion. We will see in a while that there are different kinds of systems. So continuing again, connection to lateral load system on the upper floor. LLRS on upper floor to the connection below. Connection below to the lower floor. LLRS on lower floor to the foundation connection. Foundation connection to the foundation. See, there's a difference. How these structures connecting to the foundation is critical. That's the foundation connection. The foundation itself could be the piles that Jose referred to earlier, but the connection from the structure above is critical. Remember, we said that the force in the structure increases as you go down the structure. Then we have the foundation interacting with the movable soil below. So strictly speaking, we really should consider the soil as part of the entire resisting system for the earthquake. And then that movable soil is resting on non-movable soil. Different colors are used for that part of the load path because that is below the ground. Yeah? Each item on the load path must be able to sustain the internal force. So that is how the building resists the earthquake. There is a load path, an internal river of force, starting at the floor level, going down and meeting with load paths from other floors, and they're all collecting like streams in a river going into the river. So lower down the river, you would of course get more flows. Okay, what kinds of systems do we have for resisting earthquakes? We have the typical frame. So we're talking about posts, horizontal and vertical posts. So we call those moment resisting frames. I'm not going to go into the technical reason of what is a moment. Then we have braced frames. They are characterized by diagonal members, and they can be placed in different shapes. We have X, we have what I call chevron, that is V, and then inverted V, and so on. So a braced frame is characterized by the presence of diagonal members. Then we have the moment resisting frame, and we have, of course, walls. Now, key point to note, see these little black circles? This is critical. This is how we economically get this structure to work. We deliberately cause the structure to get damaged there. Yep, deliberately. So we have this zone of deliberate damage that we call a hinge. It kind of acts like a fuse in an electrical circuit. We want this structure to get damaged at pre-selected locations. Why? This reduces the amount of materials required. Hence, the zones must be ductile. Notice ductile is inverted commas. I'll mention what that is in a little while. It's important for us to know what that is. Now, the lateral load resistant systems are ideally provided as symmetrically as possible in each direction of the building in plan. So we have a little sketch here. Jose spoke about this as well. If you don't have symmetry, there are consequences that are not quite what you would want to have. A LLRS need not be placed entirely from one end of the floor to the other. So for instance, in the long direction here, we only have our walls in the middle. We don't have it necessarily going from one side to the other. Additionally, different types of LLRS can be combined in the same direction or along the same line. So you can have walls and frames in the same direction of the building. You can have brace frames and anything else in the other direction. So you have a lot of room for conceptual design, for cutting the space of the building by using these different ways of providing resistance. When you look at the possible combinations, there are about 60 types of resisting systems in the United States building codes. Now, we are into the 7 fundamental factors, huge. If we don't have these, if we violate these, that's when we have serious problems. If we get these 7 factors correct, the only time a building will give trouble is if we underestimated the effect on the building due to the ground motion in the first place. So let us say we design for a PGA of 0.4 G, but we really get a PGA of 0.6 G. No matter what you do, you're going to have a problem. Okay, point number 1, ductility. What do we mean by ductility? Try and imagine taking a matchstick and bending it into the shape of a paperclip. Could that work? No. Why? Because the matchstick is made of timber and it will break as you try to bend it. A paperclip is made of metal, and because it is ductile, you can bend it into the paperclip shape. So the ability to bend without breaking is one way to look at ductility. A very ductile material can absorb a large amount of energy without losing its ability to support the load it is carrying. Now, in the building codes, there are 3 levels of ductility: special, intermediate, and ordinary. And that goes down. So special is the highest ductility. Ductility is ensured by the type of details used to build the structural system. So for reinforced concrete beams and columns, the transverse rebar, what we call the links and the stirrups, not the one that goes in the direction of the beam or the column, the ones at right angles, the little circly ones. Those are called transverse rebar. That is critical. Horizontal rebar for reinforced concrete and masonry shear walls. That is critical for giving ductility. When it comes to steel members, the thickness of the parts of steel beams, columns, and braces, as well as the types of connections. A more ductile system is more expensive than a less ductile system, but provides better performance in case of an overload. Now, in the Caribbean, because our seismicity is not well known and our quality control is inconsistent, special ductile construction should be used rather than intermediate or ordinary. Regularity. Now, this is a dictionary definition sort of thing. A regular building has more dependable, predictable, and economical performance compared with an irregular building. A building is regular if there is little change in its shape and strength from floor to floor, and in each of the 2 directions in the plan view of the building. Irregularities cause more complex behavior, some of which are still not well understood. They require more expertise to design and increases construction cost. Some irregularities are allowed in the code, but up to a point beyond which the building is not allowed to be used. Now we will now see, we're going to go through it not too slowly because we have to finish on time. There are 5 types of irregularity in plan view: torsional and extreme torsional, re-entrant corner, diaphragm discontinuity, out of plane offset, non-parallel systems. So we're just going to look at a few sketches that describes what this means. Jose also presented something on this. So a type 1A or B torsional irregularity, you have extreme twisting of the floors. And it can also occur for rectangular buildings. Jose was showing us that if we have stiff cores on one side of the building integrated with the structure, then although the building is rectangular in plan, you will still get significant twisting. Such buildings are not allowed in territories of high seismicity. Re-entrant corners, you see that T shape there, the re-entrant corners are pointed out here, and they have the effect of inducing complex stresses. It reduces the uniformity of movement and the stresses. It increases the stresses near the slab corners and connections. If we have a big hole in the floor, like sometimes architects like to provide light spaces within the floor, that must be considered carefully because it can introduce a diaphragm discontinuity, which reduces uniformity of movement and stress. increases stresses in the floor slab edges, between systems and connections. Continuing, a type 4 irregularity, if we look at this little blue diagram on the bottom left here, you have a wall starting, going down, and instead of going straight down, it shifts to the side and then goes down. That shift is called an out-of-plane offset. You're offsetting the lower part of the wall from the upper part of the wall. And I'm just using a wall for descriptive purposes. We can also be having the same effect in moment frames and brace frames. So the effect is that it reduces uniformity of stress and movement, increases stresses in lower parts of the building, and especially the connections. A type 5 irregularity causes complex multidimensional stresses in the building. It becomes more complex to analyze a building with such a shape. Now that is the plan irregularities. The vertical irregularities have to do with the elevations of the structure. And there are 5 types again. Soft story and extreme soft story. Jose mentioned stiff floors just now. We'll see better for the elaboration on that. Mass irregularity, geometry irregularity, in-plane offset, and weak and extreme weak stories. So what are we talking about? Vertical irregularities have to do with the elevation view of the structure. Now I'm just lumping up the forces with these red horizontal lines. A soft story, Jose was mentioning earlier on, is one that is the opposite of a stiff story. You have all of these elements above resisting. Stiffness and softness has to do with the amount of effort required to move it. Clearly, you're going to require a lot more effort to move the floors above the ground floor story in this case. That causes some problems. It can make the entire building unstable because of the softness of the ground floor story. If you have different masses, in other words, the floors are supporting significantly different weights, then we have a type 2 vertical irregularity, and that can induce non-uniform stresses throughout the whole building. A type 3 vertical irregularity is one where you have significant changes in geometry from floor to floor. So you see you have this step back on the right side here as we go up. Again, it induces non-uniform stresses throughout the building. That non-uniform stresses thing is a headache. Why? Because we have to visualize this thing vibrating. All these arrows that I draw are shown in one direction, but that's not really what is happening. That's just a snapshot. You have reversal of the force, and the force is going up and down all over the place. So this is a dynamic situation. So to calculate the stresses become complex. And we found that simplicity, meaning regularity, gives better performance and predictability. Okay, the last 2 types of vertical irregularity. We spoke of the out-of-plane offset before as a plan irregularity. Well, we have an in-plane irregularity, also a shifting of the system as you come down the building. That is a no-no because, it induces more complex stresses, reduces uniformity of stresses and movement, increases stresses in lower parts of the building, especially the connection. And then this last type 5 is similar to a soft story, but we're not talking about stiffness now, we're talking literally about strength. Common sense will tell you the more the elements you have, the stronger your story would be. So if you only have on the ground floor columns, then common sense should say that that is going to be weaker than if you have walls going from one end to the other for other floors in the same building. So a soft story is similar to a weak story in that regard. You have complex behavior induced, reduces uniformity of stresses and movement, and increases stresses in the lower parts of the building, especially the connections. Rule number 3, now that we know about load paths, what we're looking for are multiple load paths, also called redundancy. They provide more ways for the load to safely reach the ground from the floor slabs. This is good because the stresses in the parts of the system are smaller if it has more parts compared to less parts. and therefore has more locations to distribute stresses to, when a part of the system can take no further stress. In other words, you have built-in backup, built-in reserves. That is a good thing. It's considered good design practice. If there are too few parts, the building code actually imposes a penalty by requiring the system to be designed for a greater force. So as we see in our sketches here, the more elements, the better. Good practice number 4, short load paths. Short load paths avoid complex increased stresses and increased costs due to more materials required. So if we look at the example we had before of offsets, the offset is adding to the load path because the force now has to go sideways instead of going straight down. It has to go sideways before continuing. That additional load path induces problems in the building. Continuous load path. Remember, we are thinking of a load path like a river of invisible force within the building. A discontinuity in a load path is a break in the load path from diaphragm to soil. They cause spurious transmission of the loads to the structure. This can lead to unintended behavior and even collapse. Now, this is a problem that is not much appreciated in the practicing world. If you have, for instance, 2 shear walls along a line resisting an earthquake force, then you have to pay close attention to what is happening between those walls. It's called the collector portion of the diaphragm. And if this region has no provision to transfer the load to the other system, it cannot work properly. Another common one we have has to do with the connection of the roof to the walls below or to the ring beam below. We usually don't block in between where the rafters are coming down on top of the wall. And that causes gaps. Because of these gaps, the roof's rafters cannot properly transfer the roof earthquake load to the wall below. Connections, connections, connections. I can't overstate how important connections, and they're so small, it's easy to get it wrong, as Sosi was showing us earlier on for the concrete connections. A connection transmits load along the load path from one part of the system to another. The connection must be stronger than the parts connected. Connection failure disrupts the entire structure and can lead to collapse, especially for steel and timber structures. Although small, a connection is the most complex part along the load path. The diagram below shows the only automatically accepted types of seismic connections for steel moment frames in the United States building codes. Any other types must be lab tested. I saw some photographs that Gregory sent out of some steel buildings, and yeah, problems because they're not compliant with these shapes. We'll have more to say in a little while about the kinds of problems we have in the Caribbean. And rule number 7, critical. We call this the interstory drift rule. What is drift? For each floor or story, the amount of horizontal movement, called the interstory drift, divided by the height of the floor must be less than a certain amount. So if we're looking at the roof here, this is the drift. The drift ratio would be this, the length of this red line divided by the height of the story. That is critical. If it's exceeded, then glass or blocks on the outside faces of the building will fall out. And the ceilings, air conditioning conduits, etc., on the inside of the building will also fall. Part of a lateral load resisting system in a story can also become unstable if the drift is too high. In other words, if your story is leaning over, it's still carrying a force downwards, supporting the weight of the floor above. That can introduce additional stresses, and the interaction between the two can lead to instability. Excessive drift is a known source of casualties due to an earthquake, especially for steel or concrete framed buildings. Especially steel. In fact, it is the drift that controls the sizing of members for steel buildings and earthquakes. Okay, so I'm just going to mention this. I'm sure I'm close to the end of my period. This is a description based on looking at Caribbean structures over the last 20 years. This is a summary of the problems we have and what factors, what fundamentals were violated. Remember, we spoke about the 7 fundamentals. So the column on the right is saying which of those fundamentals are violated for common deficiencies shown in the left column. Typical one for steel buildings, column orientations all in one direction. That will mess up the ductility. I'm not going to go through this in detail. One of my objectives is to leave this document with you. You can use it as a reference for examining the structures in your own territories. So I'm just going to go through this quickly. So this is for steel buildings. These are some of the biggest problems. Improper wall placement. When you abut the column and the beam, we saw that that leads to what is called the short column effect. Jose was showing us how detrimental that can be on buildings. It's for steel, that happens to steel buildings as well as concrete buildings. So I'm just going to scan through this quickly. Beams have improper links, too large spacing at the ends and so on. Masonry buildings are another biggie. The biggest problem that we have with our masonry buildings, weak blocks, weak joint mortar, horizontal rebar placed in the block joint or missing, improper framing for park access, improper framing for shop fronts and so on. The solution to these problems in the Caribbean lie in training, the retrofit of existing buildings, greater communication between the architect and engineer in the early phases of the design of buildings. And that's it. Thank you for your time.
Thank you so much for this great presentation, Dr. Clark. Thank you so much, both of you, for your presentation. This is very sobering when we see some of the, when I compare some of your presentation to, you know, what we see around in the Virgin Islands, especially the building on stilts that have, you know, multiple story of stilts with it just makes me very nervous. So let me just ask you very quickly before I go and open for questions, if I share my screen very shortly. You did not address, oops, am I sharing the screen? Oh no, not yet. Okay, so I think now I'm sharing. So can you speak very quickly about these types of old buildings, the ones that are made of wood structure or the ones that are made of stone? Can one of you address really quickly the type of consideration?
Okay. Timber buildings tend to perform relatively well, including the older ones. The reason being, remember, we started off by saying that the force that the building sees is really an invisible force on the outside. That's, to get that, it's called an inertial force. Inertia is a property of mass. So timber buildings perform well because they are so light. They attract very little amplification. They attract very little inertial force on them. Their biggest weakness could be in the connections. But pound for pound, if you're looking at older buildings, timber buildings are most likely to be safer. When it comes to the stone buildings, when we just spoke about favorable performance factors and we spoke about ductility, you might think, well, stone cannot be ductile because it doesn't have anything that would allow it to bend in its internal structure. But stone can be so thick. For instance, how many times do you see churches collapsing in the earthquakes back in the 17th century and so on? There was a church that had collapsed in Trinidad. When the earthquake came in Haiti, there was a church that collapsed in Leogane, where the epicenter was. It has to be a really massive earthquake. And that's because they're using so much material that the induced stresses can take it without the need for ductility. The purpose for ductility is so that we can use smaller member sizes. So when it comes to the heavier structures, they may perform better, but the safest thing to do is to do an evaluation, and there are different levels of evaluation that can be done in order to determine how bad of a problem you have. At this point, the most, I think, comprehensive assessment and retrofit guide is the ASCE 41. And that has a section that enables you to do a visual assessment of a building. And from there guide you on what else would need to be done, whether you need a more complex assessment, and ultimately, whether you need retrofitting and how to go about doing it. Hope that answers your question.
Thank you so much. I'm going to go and ask the first question, and there was a picture of it actually, I think. Let me just share my screen again to provide the visual aid. So in this structure here, we can see somebody adding a new level on their house. And so the question that was asked was, you know, how should we consider any recommendation for concrete home where addition of rooms or in this case, new level were done? Can a retrofit be done to increase the safety of the structure?
Yes, you can do an assessment before and after to see whether you have any reserve strength that allows you to take an additional story. If you don't, then you can retrofit in order to accommodate it. But I can give you a little story about this and what I had ultimately to do. A private hospital in Chaguanas, Trinidad, they did something unconventional when designing story, and it came to the attention of the building inspector. And upon evaluation, if what they did was allowed to continue, the structure would have collapsed in the design earthquake. So what had to be done is the top story actually had to be condemned. You see, the building was originally designed for 3 stories, it went to 5 stories without changing anything. So we condemned the upper story and we strengthened the lower story. So again, it boils down to an assessment. It is possible, but it's not something that you can just guess. There are guides, some based on simple calculations. Sometimes the result of those simple calculations is that you need more complex calculations, but there are guides, and yes, it can be done.
Thank you. So I think your question is the second one, which is, you know, another question that was asked, which was, can we visually determine, you know, the structural safety of a building? And you answered that question. So thank you so much. Any other question from the audience at this point? Does anybody have any question for our guests?
Oh yeah, hi, this is Kimiko, EPA Region 2. I was just wondering, I know that the NIST did a audit of buildings after Irma and Maria, and I wasn't sure if they did another audit after the earthquakes, but based on their audits, I think they were going to make recommendations and possibly revisit building codes and whatnot. And I was just wondering if you were working, you know, with them or some other like, you know, maybe Pan-Caribbean organization that's kind of focused on natural disaster resilience in building structures.
Thank you. I think that would be Jose. Can you talk a little bit about, you know, lesson learned and after the Puerto Rican earthquake and collaboration with local and national entities?
Sure. Well, let me tell you, every time there is an earthquake around the world, there is some recognized team that go to the disaster area and they get what the lessons that they learned about that. And those lessons are introduced in the code after some research is performed. So in general, the building codes that we have from the United States are pretty good. But in the case of Puerto Rico and US Virgin Islands, we have a big problem in the sense that the last time that the seismic hazard map was updated was in 2003. So even though the code can be very good, the part of that map haven't been updated. And at least in Puerto Rico, we have found many seismic faults, active seismic faults since then, and they are not being considered right now in the building code. We found in 2012 a seismic fault that goes in a diagonal way along the central part of the island, and we estimate that can generate earthquake 7.5 or maybe 8.0 in the center of the island. And that's obviously worry us a lot. So I don't worry too much about updating the building code. I understand that the building code is in good shape. Let me tell you something important also, is that the building code are minimum requirements, okay? So in the case that for some reason the engineer, the structural engineer understand that has to be more severe than the code, is his responsibility to do it. For example, in the case of hospitals, in hospital, you don't want it to collapse, but you need the hospital to be serviceable immediately after the earthquake. So you cannot wait 2 weeks, 2 months to have the hospital ready to get the injured people, okay? So you have to be a lot more severe than the code when you are designing a hospital, okay? So keep in mind that building codes are just minimum requirements. It's just to meet the to have the lawyers happy. But sometimes you need to be more severe than that, okay?
Thank you so much. Thank you for this answer. I want to make a point that, to your point about the building code versus, the practice, the update and having updated maps of ground acceleration probabilities is very important for the structural engineers to do their work. So your point about keeping the data updated is a very vital one. That is not a building code question, but more a active research and active paying attention to the new data in the region. The second thing that I would add is the fact that in the Virgin Islands in particular, we do not. So what happens, and I think Dr. Clark mentioned it, is the ground and the soil type respond differently to the acceleration caused by a particular earthquake event. And so there is something called basically a shear velocity, which is basically either expansion of that vibration or dampening of that vibration, depending on the type of soil. For example, if you have compacted soil that you create, to build a new highway or something like that, or build a plaza, those can loosen real fast if it's not compacted in a particular way. And so in the Virgin Islands, actually, we do not have any information on how different soil respond to different vibration. That's something that, the HMP team has flagged as a very important thing in order for proper design to occur, in order for the structural engineers to properly do their evaluation. So to your point, getting data, better understanding environment is as important as getting the right building codes. Any other questions from the audience?
Yes, there's actually some great questions in the chat room. One from Cicely. one from Sicily who was asking, if a house was built in the 1950s and is still standing today after 2 Category 5 hurricanes, is there some type of inspections being done for these houses being built to be brought up to the code to make it stronger to withstand whether it's hurricanes or earthquakes? What do people do when they have these older buildings that have survived a number of things and yet you're not sure?
Dr. Clark or Dr. Martinez, any answer? What about older buildings? Hurricanes, maybe? Can a house that resisted a hurricane can resist an earthquake?
Well, at least in earthquake, I don't know in the US Virgin Islands, but in Puerto Rico, our first code that considered earthquake was in 1968. And it was a very basic code, not considering ductility at all. If her home is from 1950, most probably it doesn't take that into consideration, okay? That doesn't mean that it's going to fail, that it's going to collapse, okay? An analysis have to be performed because sometimes people build so well, even without considering any code, but people know, some people knows how to really design structures, and the house might be in good condition, but it will require an inspection and an analysis to see how it will behave during an earthquake or during a hurricane. Okay. Richard, do you have something to add to it?
Yeah, I agree with Jose. And there are specific codes that deal with existing buildings. I don't know whether you have the time to go back to one of your maps where you mentioned something like 10% 50 and 2% 50. You remember those maps that you put up?
The PGA maps?
Right. I just want to mention the 50 part. That's because when we're designing a new building, and it's a so-called normal building, we assume a service life of 50 years. If you have an older building that is existing, can you use the same code that you use to design new buildings? And the answer is yes, you can, but you're probably going to get way too conservative a result. So as Jose was mentioning, it's quite possible that an older building existing for a very long time could still work. But the special code that you use for that would take into account the existing status in terms of age. You will have to do some what is called condition assessment. You will have to estimate the actual status of the materials of the building. And then there is a special analysis. You would input that data to evaluate the building, even catering for accumulated damage due to previous events. There might have been an earthquake 20 years ago, something 10 years ago. A condition assessment can pick this up. And then you run your analysis under those existing conditions. And that is the best way to have confidence or to minimize your uncertainty about the possibilities of the building for the future. So there are codes to assist with that. They are specifically for existing buildings.
Thank you so much. I have one question for the audience. If there is anybody in the audience who is a structural engineer or works very closely with building codes in the VI, my question is, how is earthquake risk generally considered or treated? Through the permitting process or the construction or the inspection? Is there anybody in the audience who can help answer that question? Okay. Well, that's a question that we will be looking an answer for, and we will make sure to let you know. Any other question from the audience?
So there was another question in the chat room from Miguel, who was asking, would you recommend following the slope of these steep hillsides versus using stilts? Which I think I have the answer, but I trust the experts. Yeah, when people are building on the hillsides, are there any basic ground rules for the shape or the architecture to follow the slope of the hill?
Well, you can, maybe I can, I don't remember. Let me see. Puerto Rico, we use these houses on stilts, which is really very, very dangerous situation. So you can look in the web page what the a publication that we did. Maybe I can put it in again. So you can get that publication, and that will suggest you how to build some structural walls, shear walls, to support these columns, these long columns. The publication do not deal with the house by itself, but it deals only with the stills, okay? Once you have the steel fixed, most probably your house will support the earthquake, okay? But I show also a slide about how they do it in Chile. They don't use stilts at all. You know, no way, they cannot do that. They have so huge earthquakes over there, they will fall down right away. So they are building just along the tip of the slope of the hill, and they are doing that very well. That's behaved very well during earthquakes. So I think that's something that we should adopt here in Puerto Rico, and most probably in the US Virgin Island also.
Thank you. And I put in the chat, and we will put in our website, the guide. And I would love to figure out a way to have this translated into English for the Virgin Islands. So the last question of the day is not about structures, but about landslide. What about earthquakes and generation of landslide? Is there a way to predict that or prevent that?
You mean landslide?
Yes, landslides, earthquakes that can generate landslides.
That is not my area. I cannot talk about that.
Neither can I, Gregory, but I want to give an answer to the person who asks about risk and building codes.
Go ahead.
The current version of the ASCE 7, which is the ASCE 716, is now tied to risk calculation. They recognize as part of the code techniques that will allow you to calculate the risk of failure. And there is a maximum risk associated with normal buildings of 10%. It's called the fragility. And that is the risk of failure dependent on the extent of acceleration that you have. So anything above 10% is considered improper. But you have to add that uncertainty to the uncertainty of the ground shaking itself. And since 2012, the codes changed philosophy from uniform hazard to uniform risk. And the acceleration values in the maps are tied to a 1% failure in 50 years, where you are considering the uncertainty of both the structure and the ground motion. So I hope that helps.
Yes, thank you. No, thank you so much for that. And okay. Because of time, we're going to have to close this meeting. Really excellent presentations today. Lots of questions that still need to be answered for the VI, but really a lot of good food for thoughts and guides on how to start answering those questions for ensuring that we are more resilient to the impact of earthquakes. So thank you so much, Jose and Richard, for taking the time to share your knowledge with us. Thank you so much for the audience to attend this second in the Engineering for Disasters webinar series. Just to kind of give you a quick peek at the future, we are going to be organizing in the next month or so a third one called Engineering for Resilience, where we're going to be talking about what does resilience mean actually and what can we do to increase resilience of systems in general. And then another one will be engineering for stormwater, where we're going to go back to more structure-oriented and less system-oriented sort of discussion, and ask the question, how can we design to reduce stormwater and flooding risk? So I hope that you're going to be joining us. Look out for emails for those events. And thank you for joining us today, and have a wonderful rest of your week.